Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video, I'm going to do an example of how to calculate bending strength and deflection for a beam to follow up on what we've learned so far about beam design. So for now, since we haven't covered shear and we have covered compression perpendicular, but I'm going to include those later. Once we cover shear, we'll do a full design workup for a beam considering all four effects. Remembering that the four effects that we need to consider for beam design are bending, shear, compression perpendicular for bearings, and deflection. So here we're just going to focus on moment, bending strength, and deflection for now. And you'll see we have a beam that has an overhang, so it has a kind of simply supported portion and a cantilever portion. And we want to determine whether this beam is going to be satisfactory for the loads that are on it. And what load we have here is a uniformly distributed load, 5.0 kilonewtons per meter, which for the purposes of this example is all snow load. And I'm doing that just so that we save time in calculating the load combinations for this example. And we have lateral restraint only at the points of bearing. So we don't have any purlins or anything that are providing lateral restraint to the beam, which means that we're probably going to have an issue with lateral torsional buckling, and we're going to have to calculate what our KL is. Based on that, now is this a realistic case for design? If we have a uniform snow load, probably that means I have some kind of roof, and if I have some kind of roof, then that probably means I have some kind of top sheathing that's holding all of the pieces together. So that would mean that probably I do, in reality, if I had a case like this, I would have some lateral restraint. But for the purposes of showing an example of how to do KL calculation for lumber, we are going to do it without the restraint. That will also allow us to look in detail at the differences between the two spans and also calculate the deflections. Okay, so let's get started. This is an SPF number 1 2x12. So the first thing that we need to do is find our MF. And so I want to find out what is the applied moment. So I'm going to reach back, structural analysis. Actually, you know, this you probably learned even in mechanics, in your maybe second year mechanics course, is just drawing a bending moment diagram. And this is a determinate system, so it should be quite simple. And I'm going to find it in terms of actually not MF. I'm just going to find it in terms of M specified for now, which means unfactored. And then once I find the moment at my sections, I'm going to factor it at that point, which is what we should usually do when we do load combinations. So I'm going to start unfactored. And the other thing that this does for us doing it unfactored right now is that when I check my deflections, I'm going to need the unfactored loads because it's a serviceability limit state. I don't apply load factors to that. So first I'm going to find everything unfactored. And then for my ultimate limit states check, I will factor those loads and do the load combinations. In this case, the load combination is very, very simple because I only have one type of load. And for my serviceability check, which is my deflection, I'm going to use the unfactored loads. Okay, so I'm going to start by drawing my beam free body diagram. And to calculate the applied moment, I can either do it manual like I'm going to do right now, or I could use a computer program, or I can use the helpful tables of deflections that you can find in the wood design manual in volume 2 in the reference section, and I'll show you what those look like in a minute for calculating the deflections. So here's my beam. Okay, so this is my free body diagram, and using sum of moments and my other equilibrium equations, I can come up with these reactions, and I'm not going to do it all together. You can do this on your own, and I will give you the answers so you can check. This is going to be 11.25 kilonewtons, and this one is going to be 3.75 kilonewtons. Easy as pie. Simple equilibrium to find the reactions. Then based on those reactions, I am going to find the shear. Okay, so for my shear, I go up by 375 at the end. I'm using just the graphical method to do this. Then I'm going to go down by 5.0 kilonewtons per meter. Just going to kind of draw where this is going to be approximately. And once I do 3.75 minus 5 times 2, I get to 6.25 here. Then I jump up by 11.25 to get 5.0. And then I go down again by 5 kilonewtons per meter over 1 meter. And I end up back at 0. And I get a shear diagram that makes sense. Now I'm also going to look at what these dimensions are. So this is 0.75. I'm doing this by using a similar triangle approach to figure out what the relative heights are, which will give me the relative distances here. And I can get 0.75 and 1.25. So in this problem, it's not going to make a huge amount of difference. But if I was doing this problem for glulam, and I need to calculate my KZBG, my size effect factor, remember that it's the tension segment, the segment of the beam between zero moment locations, that is what defines my length for calculating size effect. So I'm going to need those lengths in general. Okay, so now if I want to calculate my moment, okay, this is what my moment diagram looks like. I will leave it as an exercise to you. If you are feeling a bit weak on calculating moment diagrams, I would strongly suggest you review it, because you will always have to know how to draw bending moment diagrams, obviously. So, I mean, for example, to find that 1.4, I know that the moment starts at 0 because I'm at a pin at this location, and then I find the area of that triangle, 3.75 times 0.75 divided by 2, that gives me 1.4, right? And don't forget as well that we need to consider the slope of the moment diagram is equal to the value of the shear diagram. So I start a high slope, I go to a 0 slope where the shear becomes 0, and then it becomes negative again as I go towards the 2.5. So try calculating that yourself. Make sure that you are competent to do that. And I can also come up with these distances. How do I find this distance here? 1.5 meters. I basically have to find where my moment goes back to 0. So I know I'm at 1.4 here. Then I have to find out how much of this triangle I need to get back to 0. So I'm subtracting area when I'm in that triangle until I get to the point where I get 0. In this case, since the slope is the same, I'm just going the same direction this way as I had previously traveled to here. So I'm going to add another 0.75, and that's where I get the 1.5. Review that for yourself. And why do I need that? In this question, I don't really need it too much. What I really need is just the actual moment values. But if I'm calculating, again, as I said before, if we're calculating KZBG, then these two would be my two segments for the calculation of KZBG. Those are the lengths between the points of 0 moment. And I would be doing that if I was, if this was a glulam member instead of being a lumber member. Okay, so then those are my actual unfactored moments. And if I want to calculate my factored moments, I'm going to go to my load combinations table for ultimate limit states. Okay, and I see these are snow loads, remember? So this is the one that's going to govern 1.5 times snow. I don't have dead, I don't have live, I don't have W. So 1.5 snow is the highest one I have out of all of these. So basically my factored load is going to be 1.5 times my unfactored load, because those are all snow loads. So if I'm saying my MF positive, for positive moment, it's going to be 1.5 times 1.4. Okay, and that equals 2.1 kilonewton meters. And positive moment here being downward deflection kind of moment, like upward concave up. And MF negative equals 1.5 times 2.5. And if you need a review of all these things, there are many other videos on my channel for structural analysis, and you can go review those yourself. They're not the primary goal of this particular course. 3.75 kilonewton meters. Now, if I'm looking at segments in terms not of not in terms of size effect, but in terms of segments of the beam that experience deflection, I have one portion, which is this portion here, which is my kind of downward deflection point part in the middle, where it's kind of my simply supported beam. And then I have my cantilever here. And those are two different places where I might want to check my deflection, but certainly where I will want to check my, I'll want to check my strength. So for those two, let's look at what the maximum moments are, because since these two, like the section in the middle here, is going to have a different KL potentially than the section here because it has a different slenderness, right? So for lateral torsional buckling, the simply supported part is going to have 1 KL and the cantilevered part is going to have a different KL. So that means they're going to have different strengths. They're going to have a different MR, right? So if they have a different MR, they also might have a different MF, right? They have a different applied moment depending on what the loading is. Now, in this case, they're going to have the same MR because the cantilever section is here. The simply supported section is here, and the cantilever section is here. And for both of these, this is the maximum value. And for lumber, we don't really need to consider positive and negative separately because the positive and negative moment strengths are the same. Remember that for glulam, that may not be the case, because in glulam, for the types of grades that are not balanced, like the ones that don't have the same positive and negative bending strength, I will have different strengths for positive bending and negative bending. So you see here 24 FE. It's not EX because it has only a strong ply on the bottom face. On the tension side face, has a stronger strength for positive bending and a weaker strength for negative bending. So in that case, I will need to have my MF positive and compare that against my MR positive, and I'll have to have a MF negative to compare against my MR negative. But that's not the case here because we're talking about lumber and we don't have that problem in lumber. So basically, my factored load is going to be this one for both center span and cantilever. Use this for this case. Okay, so this is going to be basically our MF, is the 3.75. Okay, so now that we know that MF, we can calculate our bending strength, which is what we're going to compare to that MF for both the center span and for the cantilever. Okay, so this is our bending strength equation from the standard for lumber. And for lumber, remember, there's only one bending strength equation, and it contains both size effect and lateral buckling, lateral stability effect, KZB and KL. Together, our phi is 0.9, and our FB is our small fb times KD, KH, KSB, KT. KD in this case is 1.0 because we're talking about snow load. So that's a standard term load. KH is 1.0 because we don't have any system effect happening. I would have said explicitly in the question if we had multiple members supporting the same load. I mean, in a realistic case, this may very well be a KH type of situation because presumably I have many members carrying a roof that has this distributed snow load, but in this case, we haven't stated that. So I'm going to say KH equals 1, KSB equals 1 because it's dry, and KT equals 1 because it's untreated. So now let's go ahead and find our FB. This is a 2x12, which means that we are 38 by 286. How do I find that? You will recall these tables in table 11.5 from the wood design manual, and we can get the nominal sizes. 2 by 12 is a 38 by 286, And in this table as well, you can see our S, which we're going to need in a minute, 518, sorry, times 10 to the 3 millimeters cubed. And so that's what we're going to use, but I'll show you how to calculate that as well in a second. So 38 by 286. And so let's also find our FB. So we are 38 by 286. So we are in the structural joist and plank category. So we're 6.3.1a. This is an SPF number 1. And we read across to bending at extreme fiber, strength FB, and we get 11.8. So here we're going to have FB equals 11.8. Therefore, capital FB is also going to be 11.8, sorry, MPa, because all of our modification factors are 1. The other thing that we're going to need from the table is our E, which is going to come into play when we calculate our KL. So if we read across, same table, SPF number 1, reading across to E, this is the mean E, we get 9,500 MPa. So E is 9,500 megapascals. Okay, so now we can calculate our S, or we could have taken it from that table. This is a 2 by 12, as I said. Therefore, this is a 38 by 286. All of that is in millimeters. And so our S, if you remember, the calculation for S is BH squared over 6. Y, do you remember that S equals I over Y, right? This is for rectangular section only, by the way. I is BH cubed over 12. Y is H over 2. Right? So then we cross this out, this becomes 6, this becomes 2, this gets crossed out, and I get BH squared over 6. Okay, so that's for a rectangle. Okay, so if I do that, I get 518 times 10 to the 3 millimeters cubed, which, if you recall, is the same number that they provided in the table in the design manual, table 11.5, I think it was, in the reference section of the design manual. Okay, then we need to find our KZB, which is our size effect factor. So for that, we go to the KZB table, KZ table, which is this one here, table 6.4.5, and we're looking at bending and shear, and we have a 38 by 286, so it happens to be 1.0. So in this case, not 1.0 because we're not considering size effect, it's just that this one so happens to be the one that has a size effect factor of 1.0. So KZB equals 1.0 from table 6.4.5. Okay, so now we have everything almost in this equation. We have phi, we have FB, we have S, we have KZB. Now we have to figure out KL. And you'll remember that for lumber, we have some situations where we can see if our size and restraints fit into a certain category, then we can say that KL equals 1. So let's check those requirements first and see if that's the case. So in this case, as we discussed before, there are no intermediate supports provided. I only have lateral restraints at the point of bearing. So if you recall back, if we look at clause 6.5.4.2.1, in there it gives all those categories A through E, and one with no intermediate supports is category A, and that one has a requirement of depth to width ratio of 4:1 if we want to consider automatically that KL equals 1. So what's our depth to width ratio? We have 286 as our depth, 38 is our width. That equals about 7.5, which is way greater than 4. Therefore, KL is not equal to 1. So now what do? We can now use the general method from the glulam section to find KL. So that means that we're going to have to go to chapter 7 of the standard and calculate our effective length and our slenderness ratio and figure out which kind of buckling regime we're in out of the 3 possibilities, and then use that to calculate our KL. And we're going to do that for 2 different conditions because we're going to have 2 different KLs. Okay, this is what our beam looks like if I draw it as a stick, if we remember, and we have uniform load over the whole thing. And so we're going to have 2 different KLs to check, 1 for the main span and 2 for the cantilever span, because they're both going to have different KLs because they both have different lengths. And we're looking on the left side between the intermediate support, like between the lateral supports, which are at the points of bearing. And on the cantilever side, we're looking between the last support, I should say this one, the last support, and the end of the cantilever. So we're going to calculate 2 different KLs. And in this case, since everything else is the same, we can just use the worst case one. That won't necessarily be the same for glulam if I had the same thing in glulam, because then my size effect factor might change based on location as well. So I might have all these combinations of size effect factor and KL. But actually for the KL equation, I could still just use the worst one because L is then only in one equation out of the 2. So let's start with the main span. Okay, for my main span, I need to find my unsupported length. And in this case, it's 2 meters, which is just the length of this span. If you recall, this one is 2 meters and this one is 1 meter. So my unsupported length is 2 meters. Now I have to find my effective length. And for effective length, we're going to find that in a table. And this is the table for effective length for bending members. And we're talking about the main span. So it's a cantilever. It's not a cantilever. It's a regular beam. It's a beam basically with simple supports on either end. And we have to determine which of these we're going to use based on what our loading condition is. So do we have intermediate supports? No, we only have lateral supports at the points of bearing. And what is our loading? It's uniformly distributed. So I'm going to use 1.92 LU as my effective length LE. So again, LE in this case equals 1.92 times LU. And we got that from table 7.5.6.4.3. Quite a mouthful. And if I calculate that out, I'm going to get 3.84 meters. Okay, so now I know my LE, I can calculate my slenderness, my lateral stability slenderness, my slenderness factor for lateral torsional buckling. And you will recall the equation is like this, LE times D divided by B squared. If I sub everything in, I get a value of slenderness of 27.6. This is unitless. You can see that the units are going to cancel out, millimeters squared on the top and millimeters squared on the bottom. So now I have to figure out which KL equation I'm going to use. And remember, it depends on which range my CB is in. If my CB was less than 10, then basically my KL equals 1 because I don't get lateral torsional buckling. Here it's greater than 10. It's less than 50, which is good because it has to be less than 50. But we need to see if it's less than or equal to less than or greater than CK. And so let's calculate CK. Okay, again, I am subbing in for E and for FB, KSE and KT are 1 because we're in dry conditions. So basically what we get is 27.9. Again, unitless because the MPa on the top and the MPa on the bottom cancel out. So now am I greater than, or is CB greater than CK or less than CK? It's less than CK, just barely. So this tells us which equation that we should use. So since CB is greater than 10, but less than CK, I have this KL that I'm given in the standard. Okay, so I sub everything into this equation and I get 0.681. Now, since I'm so close to CK, you could try this for yourself. If you use the other equation for CK, if you use the other equation for KL, for the case where CB is greater than CK, I should get almost the same answer because those curves are meant to be continuous. Obviously, if I increase my CB just a little bit, I shouldn't get a jump in my KL. It should be a continuous curve, even though the curves have different equations. So this then is my KL for the center span, the main span. And so I'm going to use that in MR in a minute to find my moment resistance. But first, let's do the same process for the cantilever span, which is the one on the end. And for this one, my LU is going to be 1 meter because it's this span over here. The length of that span is 1 meter. So this is 1.0 meters. And what is going to be my LE? We're going to come back to the table. Now I'm not talking about a beam anymore. I'm talking about a cantilever. I'm talking about a cantilever with a uniformly distributed load. So my LE is going to be 1.23 times LU. And if I sub that in, I'm going to get 1.23 meters for LE. And again, this is from table 7.5.6.4.3. Okay, fantastic. So I go back and I recalculate my CB. I'll point out again that all of these numbers have to be in millimeters for this equation to work. And I get 15.6, so still greater than 10. CK has not changed. Okay, since if you look back at the CK equation, I only have E, KSE, KT, those are all the same, those are material, and FB is also material parameter. So none of those have changed. So my CK is going to be the same because it's not affected by my span. So therefore, my KL is going to use the same equation as before, except with a different CB. So I should just write out again that 10 is less than CB is less than CK again. So then I'm going to use 15.6 this time on the numerator. And I get 0.97. So my slenderness has gone down, and so my KL has gone up, because since my slenderness has gone down, I'm less subject to lateral torsional buckling. So therefore, my KL goes up. My strength for lateral torsional buckling goes up. So now which one of these is going to govern? Obviously, it's the lower KL. So my actual KL is going to be 0.681. And now I'm only doing this because I know that the applied moment on both sides of the beam is the same. Otherwise, what I should do is I should calculate an MR for the main span and an MR for the cantilever span, and then compare them to the MF for the main span and the MF for the cantilever span. But in my case, if you remember, both spans, this side and this side, had the same maximum moment, which was 2.5. And the MF for that was 3.75, as shown on the right. Okay. Otherwise, I should check both separately. Okay, so back to MR. Okay, so in my MR equation, I now know all of the ingredients, FB, S, KZB, and KL, which I just calculated. And now if I multiply these together, I get MPa times millimeters cubed. Let's recall that MPa is equivalent to newtons per millimeter squared, right? It's because it's pascals is newtons per meter squared. So megapascals is newtons per millimeter squared. And this is millimeters cubed. So if I multiply those together, I get Newton millimeters. So what do I get out of here? I'm going to get whatever number I calculate, 3.75 times 10 to the 6. Newton millimeters is my moment. And if I want to get kilonewton meters, I divide by 1,000 to get newtons to kilonewtons, and I divide by another 1,000 to get millimeters to meters. And so I get 3.75 kilonewton meters. Okay, so that's now my resistance. Now, if we can compare, we'll recall that the MF actually happened to be exactly 3.75 kilonewton meters. So, wow, very lucky of us. Actually, if I used 0.680 instead of 0.681, I would have got 3.74, which would have been slightly under, probably still okay. But, you know, wow, this is lucky, but actually I just made this question up. So I put load on so that it would actually be close. Realistically, probably I'm going to certainly have some gap between MR and MF, and MR will be somewhat bigger than MF. You know, could be 5% bigger, could be 20% bigger, something like that, because my beams only come in certain sizes, and the sizes only step up. So I'm never going to really get exact match like this. So this is a bit of a bad example in that sense, that I'm very unlikely to get a resistance exactly equal to my moment capacity, my applied moment. Hopefully I'm not 100% over MR over MF, right? I should be, you know, in some kind of reasonable range. Okay, so now that we have done all that, we've checked our moment capacity and everything is great. So this is okay. And the next thing that I want to check is my deflection. So I cannot forget that when I'm calculating deflection, I need to use a serviceability ES, which takes into account if my conditions are wet. So I have to multiply E by KSEKT. In my case, conditions are dry, so ES, my E for serviceability calculations, equals E. So that's no problem, 9,500. Okay, I'm going to need my I. I can either calculate it or I can get it from that table 11.5 in the reference section of the wood design manual. And probably for now, easier to just calculate it. So I know it's BH cubed over 12 for a rectangular cross section. And I get 74.1 times 10 to the 6 millimeters to the 4th, which you can check against that table and see that it is indeed the correct I. Okay, so now how am I going to actually calculate my deflection? I could use a structural analysis program, could use SAP or something like that. In this case, I'm going to use the tables from the design manual. So I will show which table I'm talking about. Okay, so these are the tables that have all sorts of different beams with different loading conditions, and they give you what's the moment. You know, I could have calculated my moment using this instead of doing my structural analysis that I did. I mean, I just drew the moment diagram, but you see I can get the same moment diagram here. I can find out what M is, what M1 is, and M2 are just by subbing into these equations. Okay, and that is that's fine and easy. Lickety split. That would have been easier than what I did, which I did for an example. And now I can calculate also what is the deflection. Now I could also do this using moment area or virtual work or something like that, which in this case might even be a bit easier because these equations are quite long. It would be tantamount to the same thing, obviously. I'm going to use this equation. So I'm only asked in this question to look at the overhang. The reason that I did that is because this table doesn't actually give what's the maximum displacement between these two ends, between R1 and R2. It only gives it as a function of X, so I can find the deflection at any point here. If I put that in a spreadsheet, I could just vary X and find out for which place it's maximum, or I could use a goal seek to do that very easily. I'm not going to do that here. Suffice to say, for our condition, it's actually the X of the overhang of this overhang cantilever here that is going to govern our deflection. It has the highest deflection. So that's the one that I'm going to use here. So I'm going to use this equation to calculate my deflection, and then we are going to check it against the limit. So just for reference, page 940 in volume 2 of the Wood Design Manual, and it happens to be situation 30. And here is the equation that it gives. Okay, all of these should be in the same units. So I'm going to use MPa for E, I'm going to use millimeters to the fourth for I, and I'm going to use millimeters for X1, A, and L, which are all shown in here. It defines what they are. L is the length of the main span, A is the length of the cantilever, X1 is the position along the cantilever, so I want to find X1 at X1 equals A. So at the end of the cantilever, so my X1 and my A are going to be the same. And W is my uniform load that's on here, and that's about it. E and I are obvious. So at the end of my cantilever, X1 is 1,000, my L is 2,000 millimeters, that's my main span, my A is 1,000 millimeters, that's my cantilever span. My W now is what? It's 5.0 newtons per millimeter. This is my unfactored load, right? This was my unfactored snow load. So I have not applied the 1.5 factor to this number because we're checking deflection, which is a serviceability limit state. Okay, so we have to use unfactored. This was our WS, okay, which is our specified load. Okay, now if I sub that in, just bear with me. Okay, so I sub all those numbers in. Very easy to make a mistake here. I double and triple check this in my example, and I get that my delta x1 equals 0.89. In fact, I was so nervous that I was going to make a mistake in this calculation that I double checked it in the computer. So probably would have been easier just to do it in the computer. In fact, if you have a structural analysis program handy. Okay, and I get my deflection is 0.89 millimeters, and that's at the end of the cantilever. So I have basically almost a 1 millimeter deflection there. Okay, what is my limit on deflection? You recall that my delta limit is L over 180, and that's for deflection caused by the total load, which is serviceability again, so it's the total specified load unfactored. And my L of my cantilever is 1,000 millimeters, and I have 180, not millimeters, I have 180, so it's L divided by 180, and that gives me 5.6 millimeters. Now, is my dead load more than half of my total load? No, so I don't need to do my permanent deflections check because I don't actually have any dead load in this question. So if I did have a lot of dead load though, more than half of my total specified load was dead load, then I would also have to do my permanent deformations check, which was the second one that is described in the standard. So therefore, delta x1 is less than my limit. Therefore, deflection is okay. And you'll see it's much more than okay. It's very, very much under the limit. So I'm fine. Okay, so in this problem, I looked at a sample lumber beam design. We calculated our size effect, we calculated our S, we found our strength, we looked at our unit strength, we looked at KL, we had to calculate KL for 2 different spans. We potentially would have had to calculate MR for 2 different spans, but we didn't in this case just because MF, the factored load on each span, was the same. I found the limiting MR, and then we compared it to MF, and we made sure that our resistance, including accounting for lateral torsional buckling, was greater than our factored moment, which it was. And then we checked deflection using the equations in the Wood manual to help us to calculate what the deflection actually was. And we compared that to our limit, which is L over 180, and it was fine too. So our beam design is good. Later on, after we talk about shear, we'll do some more beam design examples to get familiar with the entire process.